Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 44. It's on simple harmonic motion. Imagine we take an object that's in equilibrium and we push on it. But it doesn't just move away. There's a restoring force that returns it towards equilibrium, and another returning force that returns it towards equilibrium. And so what we get is this simple harmonic motion. What would be an example of this? Pushing a child on a swing. And so there are really two examples we'll do in AP Physics. One is a mass spring oscillator, and so it's going to bounce up and down like this, or a pendulum that's going to swing back and forth like this. So equilibrium is going to be right in the middle, but these restoring forces continue to bring it back towards equilibrium. And so if you have an object moving towards equilibrium based on restoring forces, we call that simple harmonic motion. And so here are the two types we'll talk about in AP Physics. Now, an important characteristic with each of these is the period of that harmonic motion. Period is always going to be measured in seconds, and it's time. So it's the time it takes on this oscillating spring to move from here to bounce up and then to bounce back again. Or for a pendulum to swing from here over to here and then back again.
Sir Isaac Newton, what are you doing hanging out by that spring and that mass, and why is it going to the left? Yeah, it's a trap. Probably I'm filming the video sideways to make you pretend that it's a mass on a horizontal spring. So let's pretend that it is for a while, and I'm going to pull the spring to the left, and I'm going to cause then, well, I guess I've added some energy to the system, and you can see that the spring will rebound and bounce for a long time. This is simple harmonic motion, and it's awesome. Turns out that pretty much everything within some limit acts a little bit like a spring. I'd like you to take a moment and push your nose in. You notice that your nose pushes back a little bit harder the more you push in.
Ultimately, you're pushing it really hard, and your nose is pushing back really hard.
So that demonstrates that everything is kind of a spring. We can define some things for simple harmonic motion. Like, I'd like to define this leftmost point as A, when measured from the equilibrium location. So we've got A is the distance from there to there, and also the uppermost point compared to equilibrium is A as well, the amplitude. And then we can define things like period. Well, that's clearly the amount of time it takes to get from the bottom back to the bottom, and you could time that using some video analysis right now. And we could also define the maximum velocity and the maximum acceleration. We could look at the spring force. We could say negative kx and do all kinds of things. But I'm going to do that with a piece of paper. Hopefully you've gotten the idea of what simple harmonic motion looks like. And Newton is impressed. Let me just throw some knowledge at you kind of fast and furious style. We had a wall and a spring and a mass over here, and connected to the spring, and the mass was doing, well, let's put some bounds on the mass's motion. Maybe it was going to here, and it would crunch up to there, and this location here was equilibrium. At the center is equilibrium, so this distance here we can call the amplitude, and also this distance here we could call the amplitude. And we can define things, as I mentioned. We can define things like the period, and period is usually abbreviated with a capital T. So we'll put that down right there. And the frequency, well, frequency is interesting. It has units of hertz, but a hertz is the same thing as 1 per second. And so it's a rate, it's how often something is happening. And period, oh, what are units of period? Let's check that out. The units of period are seconds. So this implies a relationship. We can test it in a little bit, but this implies that frequency is 1 over period. If you guys are good with inverses, we could also note that period is 1 over frequency. This is the happiest little physics relationship that you'll ever see because it's really easy to get from one to the other. And a hertz is 1, well, it's 1 per second, but it's also kind of like 1 cycle per second, or 1 revolution per second, or 1 rotation per second, or, you know, various things like this. That's what frequency means. And we're going to have something that's a little bit different than frequency pretty soon. So you got to be cool with straight up linear frequency. The next thing is to define position. And I'm going to define the position of this, I'm going to define the position to be starting from 0, the position of the mass, starting from 0, and let's say that it's positive this direction. This is going to be my x-axis right there. And then that would be negative x. So if we do that, we can make this definition. We define the motion. I think you would find it reasonable if I made the following graph. I'll make a graph of position as a function of time. And it should look like this. We're starting at a position of A, and as time goes on, the mass approaches 0 and goes negative to, ooh, what's that value? I guess it goes negative to negative A, right? And then it will come back to 0 and go up to A again, and then back down, etc. This is a graph of a function that you know and already love. I don't have to convince you of the beauty of this function. We got A here and negative A there.